it's time to start looking at some other trends on the periodic table. So we know things like where the metals and nonmetals and metalloids are, and we know some of the typical properties of a metal or a nonmetal. But the one property that I'm really concerned with is reactivity. At the beginning of this unit, we looked at the reactivity of the alkali metals, and they're just a really goofy group of metals in that they don't have typical properties of a metal. Like most metals don't ignite when you put them in water. So I want to know, number one, why are the alkali metals so reactive? And then why amongst the alkali metals do they get even more reactive going down a group? And a lot of that will eventually be explained with Coulombs Law and this concept of nuclear charge. And we're going to relate that here to the trend in atomic radius. So atomic radius is a way of kind of measuring the size of an atom. It's hard to technically measure the radius of an atom because, I mean, electrons are in their orbitals and they are kind of moving around in their orbitals. But here's how they do measure it. They take the distance between two of the same atom. When they're right next to each other, so these are the same atoms, they take this distance from one nucleus to the other, and then they basically take that measurement and cut it in half. And then they get this average measurement for the radius of one atom. So technically radius is measured, or reported I should say, as just the distance between the nucleus and the outermost valence electrons in one particular atom. So this would be the atomic radius. But to get that number, they take the distance between two nuclei and cut it in half. And then we get a little bit more accurate measurement since electrons are kind of moving all the time. And so here's this periodic table that shows relative sizes of the atoms. Francium, big boy on the bottom of the periodic table. Francium wins the award for having the largest radius of any known element. Now, what's kind of goofy, and eventually we might want to try to explain this, wouldn't you expect maybe like hydrogen to have the smallest radius? Hydrogen is the simplest atom. It's just one proton and one electron. It doesn't even have any neutrons. But can you kind of tell, like, between hydrogen and helium, that little yellow dot by helium is smaller? And they're giving these relative measurements of picometers and approximate measurements in picometers, super, super tiny fractions of a meter. 1 picometer is 10 to the negative 12th meters. That's tiny. And so, yeah, francium wins. 260 picometers for an approximate radius. But do you kind of see that helium is just a smidge smaller than a hydrogen? That's not what I would expect, right? So eventually we might want to be able to explain that. We got to figure that out. That even though hydrogen is the simplest atom, and yes, it's the lightest atom, it has the smallest mass, the radius of helium is a little bit smaller. So it's a little bit heavier, but a little bit smaller. I am just in a quandary. We got to figure this out. Okay, so all of these trends are going to be rationalized by degree of attraction between the nucleus and the electron cloud. And that's why I'm so obsessed with Coulombs Law, because Coulombs Law lets me look at the two factors that affect the degree of attraction between oppositely charged bodies: the magnitude of the charges and the distance between the charges. So for most of these trends, there will be a trend going down a group and a trend going across a period. And so, for example, let's go down the group first. If I look at the alkali metals, lithium, sodium, potassium, rubidium, cesium, and francium. And we're concerned with the nucleus and the electron structure. And so they've got lithium, sodium, and potassium given to us in little Bohr models. And if I think about the arrangement of the electrons, I notice that they all have one valence electron. I'm looking at these guys. lithium, sodium, and potassium, all one valence electron. But that one valence electron is going farther and farther from the nucleus. In lithium, it's in the second energy level. There he is. Whoa. But in sodium, it's in the third energy level. In potassium, it's in the fourth energy level. Well, according to Coulombs Law, if you have a greater distance between your charged bodies, here we're talking about the positive nucleus versus the negative electron cloud, as you increase the distance from the nucleus to those outer valence electrons, the attractive force weakens. So here's like my positive nucleus to my outer electrons. They're farther, and it'd be even farther yet when I get down to francium with electrons in 7 energy levels. Well, gosh, those outer electrons are really, really far from the nucleus. Going down a group, this is important. Atoms get smaller by radius. I should say, what? Larger. Hello. Atomic radius is larger. Radius increases going down a group, and the main reason is that when you put those outer valence electrons in higher energy levels or higher energy shells, they're farther from the nucleus. And so the attractive force is just weaker. Attractive force is weaker. Electrons are farther from the nucleus. Atoms get bigger. The main reason why atoms get larger going down a group, and by larger I mean larger by radius, by size, it's just because the electrons are in higher and higher energy levels. They're farther and farther from the nucleus. Interesting. And we also talked about that shielding effect a little bit too, and that, not only is the attractive force getting weaker because the distance between the outer electrons and the nucleus is going to increase, but you also have all these inner electrons that block the attraction between the nucleus and the outer electrons. And you can kind of see that with these Bohr models. Like when I see potassium and there's all these inner electrons, well, those inner electrons shield the nucleus from the outer electrons. And so anything I do to make that attraction weak between the nucleus and the electrons, that's going to make the atom a little bit bigger. Ah, interesting. So atoms will always increase in radius going down a group. The main reason, the most important reason, energy levels. This guy, energy levels. Now you might be thinking, oh, but aren't there so many more protons in potassium and more electrons, and would that make the attraction stronger? I guess, but now we've got like 2 things to take into consideration. The fact that, there's more protons and more electrons, but the electrons are going in farther energy levels. And when you take both variables into consideration, it's the energy levels that wins. It's the fact that the electrons are in farther energy levels from the nucleus and more energy levels. That's what makes the radius larger going down a group. Going across. Okay, so if I go across, they give me an example of like lithium, beryllium, and then we'd skip across to the P block where we'd pick it up with boron, carbon, nitrogen, oxygen, fluorine. Here's an example of a few elements going across. Okay, so going across, I do increase the number of valence electrons. So for example, lithium has 1 valence electron. Boron has, get out of there, 2. And, oopsie, that's beryllium. Boron has 3 valence electrons. And carbon has 4 valence electrons. And so on. When I get across to fluorine, there would be 7 valence electrons. So we're adding more electrons, but do you notice now that they're all going in the same energy level? 1, 2, 3, 4 valence electrons, but they're all being put into the second energy level. So when I go across, there is not the issue of putting electrons in higher energy levels. And usually that's one of the biggest misconceptions going across. People always get the trend going down a group right, because they always they get it that, well, yeah, if you've got more energy levels, it's a bigger atom. Of course, lithium has electrons in 2 energy levels, and potassium has electrons in 4 energy levels. But yeah, the more electron energy levels you have, the bigger the atom. And we also mentioned a while ago that really it's the electron cloud that occupies 99% of the volume, the space in an atom. The nucleus is like a marble in the middle of an NFL stadium. So yeah, as you have more electron energy levels, atoms get bigger. But going across, that's not an argument, because as you add more electrons, they're going in the same energy level. So yes, there are more valence electrons, but they're all in the same energy level, so that distance between the nucleus and the outer valence electrons stays relatively constant. That's not going to be my biggest concern. My bigger concern is going to be protons. When the general distance between the nucleus and the outer energy level is the same, because all the electrons are going in the same energy level, now we look at protons. We change our focus to the charge, to the magnitude of the charge. And so, for example, when I think about lithium, lithium has 3 protons and 3 negative electrons, and they're attracted to each other. But by the time I get to like carbon, now carbon's got 6 positive protons and 6 negative electrons. And when I get over to fluorine, there would be 9 total positive protons and 9 total negative electrons, taking into consideration all of the electrons. There'd be 2 core and 7 valence. It's just a stronger magnet. The more protons you have in the nucleus, if the electrons are all going in the same energy level, those protons have a stronger attraction for the electrons. We say greater nuclear charge. When there's more protons, greater nuclear charge. That's what I want you to understand about that whole nuclear charge thing, effective nuclear charge. We use nuclear charge when we're going across a period where all the electrons are going in the same outer energy level. Well, when that's not a factor, then we look at the charge on the nucleus. As we have more protons, a more positively charged nucleus, it has a stronger attraction for its electrons. Oh, and that's then going to cause the radius to decrease. Going across, there's a decrease in atomic radius. It's because the attraction is stronger. It can be explained by changes in the numbers of protons and electrons. As you add more protons going across a period, that Z effective increases. Z effective is the nuclear charge, the effective nuclear charge. And so not only do we just want to know the general trend, that going down a group, radius increases, going across, radius decreases, but we want to be able to explain it with either going down, the distance increasing between the nucleus and the outer energy levels, and going across when the distance stays the same, then I use nuclear charge. Then as I get more protons and more electrons, that attraction increases. I'm going to put that in here too. stronger attraction. So whenever there's a stronger attraction, it's like those outer electrons are just pulled into the nucleus a little bit more than what we might expect. Here, when the electrons are farther from the nucleus, that creates a weaker attraction. And so obviously then the atoms get bigger. That's how we can explain this goofy difference between hydrogen and helium. They're just filling the first energy level, but hydrogen only has one proton and one electron, but helium has two protons and two electrons. So the distance between the nucleus and the outer valence shell is the same. They're both filling the first energy level, but because there's an extra proton in the helium nucleus and an extra electron, it creates a stronger attraction. So can you kind of see that on this chart now, that in general going down the atoms always get a little bigger, and going across they get smaller. Now going across, it's not as dramatic as going down. And there's a dramatic change going down a group because you're putting all these electrons in higher energy levels. Going across, it's not quite as dramatic. The electrons are generally in the same energy level, but they just get pulled in a little bit more each time because the nucleus becomes more positive. And so here in question 12, they want us to draw a graph. Show the periodicity of atomic size or radius versus atomic number by making a line graph that compares atomic radius across two periods. Okay, so we'll try to make this not super funky. But in general, let's say I put this dot right here. Yikes. Let's say I put a dot and I make that hydrogen. Well, from hydrogen to helium, the radius should decrease a little bit. So I'll make kind of a little line going down. So this is going to be on the bottom. I'm going to make this like atomic number, which is a way of identifying the element. Like hydrogen has an atomic number of 1 and helium is atomic number 2. And then on Y, this will be atomic radius. Okay, so now if I think about helium versus lithium, well, in lithium, the electrons are distributed amongst more energy levels. Lithium's got electrons in 3 energy levels. So lithium is going to be maybe like up in here. Get out of there, you booger. So maybe I make this lithium. When I add another energy level, the radius should increase. But now as I go across from lithium to maybe like beryllium, stinker, and then across to boron and carbon and so on, nitrogen, oxygen, fluorine. I gotta put them closer together. And maybe neon. Now they should go down in radius. And so I'm gonna say this is neon. Now I know they only say going across 2 periods, but let's be an overachiever and go 3. Because now if I go neon to sodium, now sodium's got electrons at 3 energy levels, neon only has electrons in 2. So there should be a big jump again. So I'm going to go like maybe up in here. Whoa! And I'm going to make this sodium. But now as I go across from sodium, magnesium, aluminum, as I go across, the atoms should all decrease in radius again. So sodium, and then maybe this is like magnesium, aluminum, silicone, stinker, and then phosphorus and sulfur and chlorine and argon. They should all get smaller going across. So here's the 2 things that I want us to be aware of on a graph. If I go down a group, so here's like my hydrogen, my lithium, my sodium. Going down a group, the radius increases. But as I go across, the radius should decrease. So if I go across from like lithium down to neon, well, that decreases. Sodium down to argon, that decreases. Going across, as I have more protons in the nucleus, the attraction gets stronger, the atoms get smaller. But then the trend is, this graph says, hey, not that bad. The trend is even apparent on our little graph in the noble gases, because there should be helium and then neon and argon. They should get bigger going down a group because of the increase in energy levels.